Chapter 15 is a more in-depth chapter, and make sure you have pen and paper while listening to this lecture, because some of these problems will require you to work through the math, and if you understand the math, you can understand the concepts. So let's take a look. We've talked about random variables before, and we're not so focused on random variables. These are denoted with a capital letter X. What we are primarily concerned about is discrete random variables. Now, a discrete random variable will be denoted with a lowercase x. So what is a discrete random variable? What is it? Well, it's only whole numbers. So examples of this would be things like the number of students that come to class, the number of people out of 10 who believe in ghosts, the number of subs sold daily from Subway, number of goals in a soccer game. So all of these things right here, they would have to be whole numbers. You can't get half a goal. You can't sell half a sub. Well, people say you can, but you're really selling a sub still. So it's like if Subway said we sold this many subs, they might have how many footlongs or how many 6 inches, but still a 6-inch sub is a sub. So with this in mind, these are whole numbers right here. Everything right here is a whole number, a discrete random variable. When we think about these distributions, we can actually make a probability distribution. And this is the collection of all possible values of a random variable. So what we need are similar to our rules before. Our rules before were that the probability of x, which we have stated below, right here, the probability of x is greater than or equal to 0. And we could also state it's less than or equal to 1. This means it either never happens or always happens or somewhere in between, and that's for all discrete random events. If we were to add up all the discrete random events as we see down here, this says the sum of all discrete random events, the sum of all the probabilities of the discrete random events is equal to 1. And that basically says something must occur. Like we can list all the events, and one of those events must occur. That is all we're saying right here, is that the events have probabilities between 0 and 1. Add them all up. If you have every single discrete random event, one of those must occur. So let's go back and look at the distributions from before. One of these things must occur. We could list out, the number of people out of 10 that believe in ghosts. And it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we talk to 10 people, somewhere in between 0 and 10 people must believe in ghosts. You can't say 11 people believe in ghosts if you talk to 10. So we can actually make a probability distribution by finding out the probability that 5 believe in ghosts, 6 believe in ghosts, because the probability 5 or 6 believe in ghosts, 5 believe in ghosts, or 6 believe in ghosts, will have an actual probability associated with it. So we have met the criteria. So let's go ahead and look at a coin flip here. This is more specific, and we can see the probability mass function right here. This is what this is. A probability mass function lists out all the probabilities associated with the discrete random event. As we said here, the discrete random event is x, lowercase x right there. So with this in mind right here, we have the probability of getting 0 equal to this. We have the probability of the discrete random event being 0, the discrete random event being 1. And when you think about this, if you flip a fair coin, the number of heads that you get will be either 0, 1, 2, 3, 4, or 5 if you flip it 5 times. The most likely events, just flipping a coin, are 2 and 3 to get it for heads. The least likely events are 5 and 0. And interestingly enough, this distribution is symmetric. If you notice, it's very high here in the middle with great probabilities for 2 or 3, but lower probabilities for 0 and 5. It's an interesting distribution that way. And this is valid because all these probabilities are between 0 and 1, and they add up to 1 total. So this is a valid probability mass function for discrete random events. Excellent. So what is expected here? Well, in our previous example, we'd expect something like 2.5, which is weird to say. That's very weird because that's not a discrete random number. 2.5 is not discrete, but still it's somewhere between 2 and 3. So what we expect is not actually the discrete number that we will get. So we could say we expect 2 or 3. That might be more true to the discrete numbers. Over here, when we talk about the number of students that come to class, if we're in a class of 100 people, we might expect about 70. Number of people out of 10 that believe in ghosts, we might expect 3. I haven't talked to people about ghosts lately. So you can kind of think of some numbers here down below, but it would all be based on your knowledge of the distribution. We are going to call the expected value mu, or e of x. This means the population mean. Mu, we've seen it before. We'll see it a lot more in the future. The population mean is what's going to happen in the long run. So if I go out and I start flipping a coin, if I flip it 5 times, I might get 0. I might get 5. But if I keep doing this and I start looking at over the long run, well, usually when I flip the coin, I'll be more likely to get these events because they're at the average. So the mean is what we observe in the long run. This is very similar to our law of large numbers. So you will observe this mean after multiple trials. So we're also interested in the standard deviation right here. Remember, we have the mean and the standard deviation from normally distributed data. And we're going to see that a lot throughout this lecture. So what we're going to do here is we're going to look at some examples where we know the probability mass function. And with this in mind, we're actually going to be able to describe it. So let's go ahead. As it says in the material that follows, we will assume that we do know the probability distribution of a particular discrete random variable. And so we will be able to calculate the expected value and the standard deviation. We will then use this expected value and standard deviation to help us define what are unusual or rare outcomes. So what does that mean? What it means is when we look at this, we're going to be able to tell if something's an outlier. And you should know what that means right now. An outlier is generally 2 or 3 standard deviations away. Sometimes 2, we consider that to be a light outlier, or a lot of people might just consider that an outlier. 3 standard deviations away, that is no doubt an outlier. So with this in mind, let's start looking at some examples here with ghosts. Going here, we have the ghost example. So we have 2 separate polls here. One poll was of 889 people, and 40% said they believed in ghosts. One was 808 people, and 48% said they believed in ghosts. Are any of these surprising to you? Does it seem odd? Well, they're both kind of close, and they both have similar amount of people. But what can we garner from this? Well, we have the population of all people, all U.S. adults. And then we have these small samples. What we're getting from the small samples are p hat. This is p hat, which is the sample proportion. What we wish we knew is the population proportion. This is a very important notation part right here with p, the population proportion, and p hat, the sample proportion. Make sure you know those because we're also going to talk about y bar and mu of y. This just stands for the mean of variable y. A lot of times you might just see mu, so mu would just be mean. And sometimes they associate it with the variable, but it would still just be the mean of variable y if there was no other variables. So mu is the population mean, and y bar is the sample mean. P hat is the sample proportion. P is the population proportion. Very important to know that notation right here. We've seen this before because when we looked at people making free throws, we looked at kind of the idea of 50 attempts when we would expect 75%. This is where we flip the coins. The population proportion should be equal to 75%. Well, that's what is expected, but not all the sample proportions are going to be equal to that. When we look at it in the long run for our classes, we saw 330 simulations, and the average, this is not a quantitative mean, it's the average of all the proportions, the sample proportions, was 74.8. But we're literally setting this up with coins to be 75% because we had 2 coins and we set one instance where it would be a missed free throw. So we should see 75%. Is this weird? I mean, this is close to 75%. And I want you to understand something about this graph. These 330 observations are the proportion, each one of them represents a proportion of made free throws for 50 attempts. So it's not like one attempt, because you can't say I made 75% of one attempt. This is in one attempt. Let's see right here. If someone landed right here, it would be in this bin right here because the bins go from left to right. If someone had 75%, then in their 50 free throws, well, that would be impossible because they'd have to make 37.5. So they could have 74% or 76% with 37 out of 50 made or 36 out of 50 made. 36 out of 50 is 78%. Am I doing that correct? Let's think here. 36 out of 50. I meant to say 38 out of 50. That's where it didn't sound right for a second. 38 out of 50 is 76%. 36 out of 50 is 72%. And they would fall over here in this bin then. And that's where these numbers are coming from. These 330s are 330 attempts at 50 free throws. So this is an interesting graph because we're seeing the long run. Looking at this example right here, you'll notice that the numbers we're sampling from are 1, 2, 4, 5, 7, 8, 9. We are interested in the proportion of odd numbers in a sample size of 5. So when we look at this right here, we would expect, and if you look at this, the odd numbers up here, there are 1, 2, 3, 4, and that's out of 1, 2, 3, 4, 5, 6, 7. So that's 4 out of 7. As it says down here, the population proportion is 4 out of 7 odd numbers. When we do the simulations, we find out that we actually get 57.1%. We actually got lucky down here and found the same proportion of odd numbers in our samples. If you notice, it kind of fluctuates down here. We do sometimes go a little bit high, and then other times we go a little bit low. But actually, our simulation shows that we're going to observe the true proportion or close to. And think about this. In this example, we observed the true proportion or close to, and in the previous example, we observed 74.8. That's about as close to 75 as you can get. I mean, if I told you I'd give you $74.81, you'd be like, okay, that's basically $75. So we're noticing that we will observe the true proportion a lot of times when we do multiple sample proportions. So let's talk about what's going on here. We're looking at the distribution of all possible sample proportions. This is called the sampling distribution of the sample proportions. I want to make this clear. We are looking at, right here, a distribution of sample proportions. That's what this is. This graph is made up when people attempt 50 free throws, and then they put their observation in here in this bin. As in, a lot of people landed in this area. You can see there's 100 observations here and there's 80 observations here around. It's a little bit more than 80. There's like 85 because that's where it lines up in the count. So there's a lot of people who made between 75 and 79.99. There's a lot of people who made between 70 and 74.99%. This is a lot of percentage of people fell in here when they did their 50 free throws. This is a distribution of the sample proportions. Very important what we're making here. So what we have for these distributions is we have the expected value, which is the mean of it, and the standard deviation. This is the expected value of the sampling distribution of p hat. This is the standard deviation of the sampling distribution of p hat. All this is right here is a mean and a standard deviation for your distribution. We've seen this before with the normal model. We're going to say it has a mean of blank and a standard deviation of blank, and we're going to assign formulas to it. So here we go. The formula for standard deviation, as I always say, is p times q over n square root. That's p times q over n square root. The standard deviation for the standard deviation for the sampling distribution of the sample proportion. Very important right here. We are going to use a known population proportion. A known population proportion and the known complement of the population proportion. If p is equal to 0.8, q is equal to 0.2. N is just the sample size. We will have conditions that we'll go into more in depth in a moment here. So we'll look at the conditions in a moment, but for now, the important part here is the standard deviation of our approximation with the normal will be p, which is the population proportion, times q, which is the complement of the population proportion, over n square root. Do not use p hat for this. That is a common mistake people make, a good way to trick you on the test. We need to use p and q. So what does this mean for our free throw example? Well, we know that we should expect to see 75% made free throws, and that's where the mean comes from. The mean is just the population proportion. We need to calculate the standard deviation. So this is from our simulation down here. And let's see here. P times q over n square root. P is 0.75, q is 0.25, over n, let's times those, which is 50, and then we can hit square root, and what do we see? The actual standard deviation is 0.06123, and from our simulation we got a very close number. This is the actual kind of theoretical from what we understand about the distribution, and this is from our simulation, so it's an estimate. So we get something very close to the in-practice example. When we simulate results, we basically find what the theorems say we should find, what the formulas say. So we are very, very close to that right here. For these things to work properly, we actually need to check some conditions. Because what we want to do here is we want to state that the sampling distribution of p hat is approximately normal with a mean of p, which is the population proportion, and a standard deviation of p times q over n square root. Can't say that enough. P times q over n square root. What this means right here is we can use the normal. And that's the best thing. As you can see the exclamation point, we can use the normal. We love that. Using the normal is one of the best things ever. Because what do we know? We know the 68, 95, 99.7 rule. That is one of the most amazing things we have because it lets us understand what percentage of data we would expect to be within so many standard deviations. One thing we need to make sure happens here is that NP and NQ, that's just Q right there, 1 minus P is Q. NP and NQ are both greater than or equal to 10. Now in some notes they might say greater than 10. Personally, we've always said we don't care if it's greater than or equal to or equal to 10. 10 is good enough, 10.1 is better, but we want these things to be greater than or equal to 10. What are these things? What NP and NQ are, it stands for, instead of the proportion of successes from your population, it's the number of successes. So if I go out and talk to 100 people and I say, do you play Xbox? I need 10 people to say yes, this is number of successes, and 10 people to say no. Now I could have 80 people say yes and 20 people say no, and that would satisfy it. I have at least 10 successes and at least 10 failures. And it doesn't matter what you call successes and failures, it just means 10 of one group and 10 of another. Because we're asking people a categorical question right here, a yes-no question. When we do this, we get this beautiful distribution that we've seen 100 times, the normal distribution. And this is where we can do our classic 68, go in between 68, 95, and 99.7. That's why we love the normal. And if you notice here, it looks complicated, but it's not. All we see here is the mean of p, which we stated before, a mean of p, right there. And then we see we're going down 1 standard deviation, 2 standard deviations, 3 standard deviations, p minus 3 standard deviations, p plus 3 standard deviations. Why is this a standard deviation? It's what we're calling a standard deviation, p times q over n square root. And there it is there again. Does this look normal to you? It actually is pretty normal. If we were to do a goodness of fit test, I actually do believe this would pass as a normal. It might look a little bit weird, but that's probably just due to some weirdness on the bins. As we know, we can change the bin sizes. You can see a little bit of a left skew here because the mean, that actually is the mean. Very few people know that. There's the median, and the mean is being pulled down. It has some outliers. Maybe some people didn't do the simulation properly, but it looks kind of normal. So here we see all the math, and I did part of it before. We see the p times q over n square root, and we see the mean of 0.75. This is our theoretical kind of what we would expect. It's the normal model right here. And the relative frequency. No longer do we have a count like we did on the previous model. This would be just a frequency. And then over here we have the relative frequency, which is in percentages. And yeah, we expect a lot of the times around 12, 14% of the time, 12, 13% for people to get around 75%. It's pretty common. A 75% free throw shooter should shoot 75%. The other numbers down here are going to be less common. My cursor was going away there. So we see this as we go so many standard deviations away. We can even compute what would be 2 standard deviations above. So we can just go here and times 2, and then add that to 75.75. And 2 standard deviations above would be 87.24. So if they shot 88%, that would be kind of an outlier. We'd say, whoa, you had a really good run there of 50 free throws. And remember, this is the proportion of made free throws out of 50. This is the sample size right here. So this distribution, very important, is relative to the proportion they make out of 50. If you'll notice, the standard deviation would get smaller as n increases. And think about this. If I were to go out and shoot 1 free throw, do you think it'd be I can't even make 75%. It would be hard to, you'd have a lot of 0% and 100%. This graph would look crazy, and we wouldn't pass the success failure condition. That's why we couldn't use the normal. So we violate, you can't have 10 successes and at least 10 failures. Now, if I were to go out and shoot 1,000 free throws, and I'm a 75% free throw shooter, pretending that I don't get fatigued or anything, we would probably see close to 75%. It'd be very odd if I made 60% because I would make 600 out of 1,000. You'd be like, well, I don't think you're really a 75% free throw shooter if you make 600 out of 1,000. You know, we could pretend I don't get tired, but that could probably play a role in it. But this is what we expect for a 75% free throw shooter for 50 free throws. And you can see what would be odd. It'd be 2 standard deviations down this way, or 2 standard deviations above. And you can find that simply by adding on or subtracting standard deviations. So right here, what do we get for the ghost problem? The ghost problem we talked about earlier. Well, let's pretend that 45% of the US adults believe in ghosts. If we go out and sample 808 US adults, then we would expect to find 45% believe in ghosts. And we would expect a standard deviation of about 1.75%, right there. So let's go ahead and graph this. This is what it looks like. Now, if you notice, we're just adding on the standard deviation. This is all the formulas on it. Here's your mean, standard deviation. And we just assumed that the mean was true. This was let's hypothetically say that 45% of Americans believe in ghosts. Is our 48% figure really that odd? And the answer is no. You can literally see by graphing it that it falls within 2 standard deviations. Just visually inspecting it, it looks to be about 1.8, 1.82 standard deviations. And let's go ahead, I think it might show it in a slide or two. We can actually go ahead and find the z-score for that. A z-score is always observation, which in this instance is 48, minus mean, which was 45, divided by standard deviation. We're using the same formula, observation minus mean divided by standard deviation. And I was wrong in my estimate, but I was close looking at it. It's 1.714. And yeah, that's not an outlier yet. It's large. It's a little bit odd, but we're not going to call it odd. We're going to stick to above 2 or below 2 standard deviations is odd. So this isn't really that odd given a sample of 808 people. We use our 68, 95, 99.7 rule once again because we can see right here 2 standard deviations, 95% would be between this. And we're going to call anything outside of it an outlier. Great, amazing rule right here. It comes into play so much. And we can even find where 2 standard deviations would be. You can see it right here at the bottom. And you can also see it graphically right here at -2 and +2 standard deviations. There's the z-score calculation once again. I just wanted to make sure we had it, and we saw it. So these results are not that odd. The z-score is not large enough for us to say it's unusual. With this in mind right here, it's only approximately normal. We need to make sure that we meet some conditions for this. And here's our conditions to make sure it's normal. We need to randomly select these. And if you think about it, if they go out and talk to people at a skeptics convention, that's not a random sample. So we need to randomly call up people. We need to do a simple random sample to bring back an old topic. We simple random sample people, pick open a phone book, select random names. We don't get bias, and we make sure we have a random sample of US adults. The 10% condition. Now, people hate this condition. It's a very odd one. It has to do with the way we calculate our statistics. If you want to know exactly what it means for testing purposes, don't sample more than 10% of the population. If you want to go more in depth, we actually get error. There's a great AP article on it, AP statistics article, regarding when you use these calculations. Sampling too much of the population starts to increase the error we observe in our calculations. And so they become less reliable. It's the way the math works, and people have shown this time and time again. So it sounds weird to say don't oversample, but this is kind of considered the oversampling condition. It's a great way to test on it because people think, oh, sampling is good, and it is. But your statistics become less reliable, and you can't really trust your numbers if you go over 10%. If you get 11%, it's not the end of the world. If you get 9%, it's not like it doesn't have some bias. It just starts to exponentially go up as you get more and more. Like 10 is bad, 15 is really bad, 20 is horrible, 25 is crazy, and your statistics become less reliable. So don't sample more than 10%. For example, UT has around 30,000 students. Don't sample more than 3,000 or you've oversampled and broke the 10% condition. The success failure condition. This is what we talked about earlier. NP and NQ need to be at least 10. And so if they're 10, that's great. We'll never put on a test where they're exactly 10. It's like 10 is good, 10.1 is better. You just want there to be at least 10 successes and at least 10 failures. If I go talk to UT students and I say, do you think we'll win the national championship this year? And I wanted to find the true proportion of students that believe that. Well, I'd need at least 10% to say yes. Excuse me. I'd need at least 10 to say yes and 10 to say no. These are actual students saying yes and no. These are what we consider number of successes and number of failures. At least 10 successes and at least 10 failures. So when we meet these conditions right here, we're saying that it's approximately normal, that we can use the normal model. These are very, very important conditions, and they're going to carry on throughout the course. Random and 10% are in almost everything in the remaining conditions. I always ask people in class, what's condition 1? They say random. What's condition 2? 10%. And hopefully they can tell me what those conditions are. These are pretty much the first 2 conditions for a lot of our tests to come. So with this in mind, of all cars on the interstate, 80% exceed the speed limit. What proportion of speeders might we see among the next 50 cars? And so take a moment right here and see if you can figure it out. We want a mean and standard deviation. So pause the video and see if you can get the mean and standard deviation. Let's take a look at it. Okay, I hope you paused the video and given it a shot. So the mean is going to be, well, if apparently 80%, that's the mean. And you can draw this out. You can draw the normal curve and draw a mean at the center of it. Now to get the standard deviation, we need to do P, which was the mean, times Q, which is 20%, over N, which is 50. And then, whoa, I hit it one too many times there. P times Q over N, and then we hit the square root. And magic. This is the standard deviation. So thinking of this, if we times it by 2, it's about 11%. So you can go plus or minus 11% from 80. And, we could say 95% of the time we'll see between about 79 to 91%. And considering we need to check the conditions, did we do this randomly? And the at least 10 successes and at least 10 failures condition is so close on this, because 20% of 50 is 10. So it passes just barely. And that would make a weird test question. I would say it passes. Is 50 cars less than 10% of all cars? I'd say so. I think there's more than 500 cars on the highway. So we're doing well on that. You don't know it, but 52% of voters plan to vote yes on upcoming school budget. We poll a random sample of 300 voters. What might the percentage of yes to no yes voters be in our poll? So let's take a look at this. We would expect, given that it says we don't know it, but that's what's going to happen, or that's the expected value. So let's go ahead with that being the mean of our distribution, find the standard deviation, times it by Q, divide it by the sample size, and then square root. And we get close to 3%. I am doing a little bit of rounding, but let's times it by 2, and it's 5.7%. So if you add and subtract this, you would find out your 95% kind of area of what to expect. We'll do some confidence rolls soon, and we'll see this come up again. So you'd expect 52 plus or minus 5.7%. So yeah, we would probably observe that it would pass, because we could observe lower than 50%, but a lot of this interval is above 50. Let's do the last one here. A manufacturing company produces AA batteries, and it is known that 0.2% of their output is defective. So if UT orders 25,000 of these AA batteries, how many might be defective? Well, we would expect 0.2%, and so you have to write 0.2 that way. It's 0.0002. And now let's check our success condition first. The number of successes, and that is correct, is 50. 0.2% of this is 50, and we pass. So let's go ahead and do P times Q. P times Q over N square root. I say that so much. So there's P times Q, and then we need to do over N, and then square root. And this is I'm going to write out 283 when you round it. It's 0.000283 when you round it. And that's 0.02%. So when you times this, it's going to be very close to 0.05%. This is a very small number. It's very close to 0.05%. So it's really 0.2% plus or minus 0.0566%. Very small, but we should see about 0.15% to 0.25%, somewhere in about there. I'm doing a little bit of rounding, but this is what we kind of expect to see here. There's some great examples here. I love this example because you can think about what you could actually do at a casino here. A dice roll, we know the PMF of. The probability mass function of a dice roll is 1, 2, or excuse me, the discrete random events to start are 1, 2, 3, 4, 5, 6. Each one of those has an associated probability of 1/6. So when I roll a dice, I would expect to get 6.1667% of the time. That's 1/6 right there. So if I roll a dice 100 times, we can actually look at the distribution. And I thought we had it up here, but we don't. But let's look at the distribution. The distribution right here is going to be a center of 0.166, and then we need to times that by 5/6, which is 0.833. We're just doing P times Q over N, which is 100 dice rolls, because we're going to roll it 100 times to see how many times it comes up. And then we are going to square root. This is the standard deviation right here. I found the standard deviation for the proportion of sixes we would see. So let's take a look at this with the David M. Lane applet. Okay, we're on the David M. Lane applet, and let's go ahead in here and put in our mean of 0.166x and our standard deviation, which I've just copy pasted. Now if you remember, we're trying to see if this dice has a problem, if it's coming up a weird amount. In our problem, it says that in our 100 dice rolls, we observed a sample proportion, look at that, p hats back, sample proportion of 0.31, which was 31 out of 100. That's the sample proportion, which is just calculated by number of successes over number of trials. 31 out of 100 is 31%. So is this odd? Well, we don't even need to get the z-score because look, 31% has a z-score above 3. And all this applet does is put in the mean and then add on the standard deviations each time. And the z-score is probably close to, we could find it out exactly if we wanted, take observation minus mean over standard deviation. All we're doing is observation minus mean over standard deviation, which is z-score, and it's 3.84, which falls over here, and we can see that. So this dice is rolling exceedingly high. There is a problem with this dice. We would say that the probability of this is extremely small. We could find this out. We can simply click above right here and type in 0.31, and on my results it's probably going to say basically 0. Basically, I mean it's a 1 in 10,000 chance. So he's saying no, it happened randomly, I swear, 1 in 10,000. Yeah, it could happen, but no, it doesn't seem likely. So with this in mind, I would say that the dice is not fair. Go over this example. A lot of these examples so far have been really the math you need to understand to get this down. And we're going to now talk about this same topic and use means next. Because when we do this with means, we're going to see the exact same idea here. We're going to know a population mean, and then we're going to see what's called the central limit theorem. So let's do this with quantitative data where we're doing it with a mean. So we can compute from a random sample here and have a sampling distribution. Let's look at actual dice rolls again. So when we roll a dice, what we would see is kind of a distribution that looks kind of flat. But what if, think about it for a second, a distribution of dice rolls would look flat because 1 would come up as much as 2 would come up as much as 3 or 4 or 5 or 6. But why do these not look flat? These don't look flat because what we're doing in this one right here is we're averaging together 2 dice rolls. This distribution right here is the average of 2 dice rolls. So how would you have to get 1? To get 1, you would have to get 1, 1. To get 6, you'd have to get 6, 6. In 3 dice rolls, how would you have to get 1? You'd have to get 1, 1, 1. How about in 20 dice rolls? Well, to get 1, you'd have to get 1, 1, 1, 1, 1. You'd have to get all 1s. So what's going to happen? Look at this. It's going towards the center. And what do you see each time? It's looking more and more normal and more tighter. Because imagine this. You walk down the street and you talk to one guy and you ask him, how tall are you? Would it be weird if that one guy was 5'8" or 6'8"? I mean, you'd say that's kind of weird. But what if you talked to 100 guys and they were all 6'8"? That'd be really weird. You'd be like, that's a basketball team or something. That's really weird. And what we're seeing here is when you take multiple observations and average them together, you're going to find something near the mean. If you talk to 100 guys, and you average their height, you'll probably find something close to 5'10 or 5'11. One guy could be much more variable. We see down here we're just averaging 2 people. There's a lot of variation, but when you average a whole bunch, it gets tighter. So how is this going to equate to us? Well, what we're going to do here is we're going to use the normal distribution when n is large enough, because this is going to allow us to say that the distribution is going to get tighter and more normal. This is called the central limit theorem. The central limit theorem is the idea that as we look at a distribution of means, we can describe it with a normal model when n is large enough. This is the distribution of all possible sample averages. Going back here and looking again, these distributions right here are not individual dice rolls. Any observation inside of here that makes up a part of this bin, and this one was obtained from 20 dice rolls, and this one was obtained from 5 dice rolls. These are not individual distributions, these are sampling distributions. Very important to what we're doing in this lecture. So going over here, let's look at the fundamental theorem. What we need to understand is that this is an approximation of the normal. We will need to have a large enough sample size. I can't reiterate that enough. We have the same sort of conditions again. Random, 10%. We've talked about those a lot. Same conditions right here. But we have a large enough condition. The large enough condition right here says that the more non-normal a distribution is, and when you think about it, non-normal means it's not mound-shaped, it's not the pretty mound shape, the larger the sample size needs to be. 25 works for most everything. 100 literally works for pretty much everything. 100 is kind of this is large enough for everything. 25 is, okay, it looks kind of a little bit weird. Because what did we see? The distribution becomes more normal. So if it's really normal to begin with, well, like this one's pretty normal, and you look like, does that look normal? Yeah. It was kind of normal to start, and it turned pretty normal out. So that we didn't need, we were fine at 20. We were probably fine at 5. But 25 is your kind of good enough for most everything if you want to be safe, and 100 works for everything. But I want to reiterate this, and this could be on the test. If a distribution looks normal to begin with, the distribution of sample averages, even for sample size 1, will be normal, because the original distribution was normal. Increasing n, as we see here, makes it more normal. But if it is normal, then it'll be normal at sample size 1, which is still the original distribution. It only makes it more normal. So if it is normal, it doesn't need to become more normal. So let's go ahead and look at this in practice right here. We are going to use the mean of y bar to be equal to the mean. The mean for the sample means is equal to the population mean. This is what we expect. We expect the sample means to have the population mean. We expected the sample proportions to have a mean that was the population proportion. Remember this. We had a 75% free throw shooter. That means we expect, on average in our sample proportions, to be 75. Same thing with dice. We expect the average to be true to the population average. So how are we changing up the standard deviation now? Well, the standard deviation kind of follows the same formula. Before we had a normal model with a mean and standard deviation. Now, with quantitative data, we have a normal model with a mean and standard deviation divided by the square root of n. Now think about this, divided by the square root of n. That's going to make this smaller as n gets bigger. And just look at this. Going back slides here, what happens? Do you see? It gets more normal and tighter, I said. Tighter each time because it's getting divided by the square root of this. That's all that's happening here, is it's getting tighter by a factor of square root of n and becoming more normal. And that's the distribution of sample means. So with this in mind right here, we can use this applet right here, which I'll show you right now. This applet is amazing to use because it shows exactly what we're doing. So let's take a look at it. Okay, let's begin this applet. Okay, this is our distribution of pure quantitative data. It has a mean of 16 and a standard deviation of 5. I'm going to sample a sample size of 2 from it. So I'm taking 2 observations and averaging them. This is a distribution of a distribution of sample means. This is the parent population, the individual values. This is a distribution of means of sample size 2. Take 2, average them. You see how it falls right between them? Average them. And what if we did this a whole bunch? You see how it's building up? And watch this. It's normal. It's also tighter. You can even check the math. There's the new standard deviation. Well, let's take 5. Well, first, on this calculator, we take square root of 2. And I should have known that one. That's an obvious one. 5 divided by square root of 2. 3.5355. And I bet you 3.5355, watch this. As I do more and more observations down here, more and more, actually I think that's what it rounds to. Yeah, that rounds up to 3.54. This is a simulation that's not trying to get, it's not trying to make this number happen, but it will, because this is what happens when we do this. This is what the central limit theorem tells us. It's been proven, it's a theorem. So now let's look at what happens with 10. Oh, 10 is, well, no, let's not do 10, let's do 5. Why 5? Because what is the standard deviation divided by the square root of 25? It's 1. 5 divided by square root of 25 is 1. And let's watch 25. This is 25 observations. And if you notice, my distribution before was normal. This distribution of sample means of sample size 25 will also be normal because my parent population was normal. That's how we get one observation. One observation now is the average of 25 individual points from this population, this parent population. And as I said, if I did this a whole bunch, the mean stays the same and the standard deviation is now 1. It's a lot tighter. So we showed that we don't need a big sample to make a normal distribution stay normal. But what about if we take something all kind of weird? Now this is not a normal distribution. This distribution looks crazy. What happens if I take a sample size of sample size 2? Well, it's going to take 2 points. If you see, it's not going to look really normal, is it? Watch what happens. That's not normal. Not normal at all. So we see that the standard deviation got tighter, and we see that the mean is pretty much still the mean. Probably if I do some more simulations right here, see if you watched it go to 8.8 and 8.7, it's not, it works. It's amazing what this will do. But let's try this. Let's go to 25, and we might need something higher than 25, but let's see it. Once again, it's taking all of them again, so we'll speed up time here. Will it work? It did, basically. You can still see a little of that right skew, so maybe we needed something higher than this. But if you notice, it is at the mean of 8.07. The standard deviation has gone down by basically a factor of 5, actually nearly perfectly a factor of 5, because it's 10.8 divided by the square root of 25, which is 10.8 divided by 5. This is the central limit theorem. Take a parent population of individual observations and then average together multiple observations to make a distribution of sample means. This is how we're obtaining the sample means, by averaging together multiple observations for one observation down here. And this distribution will be more normal and tighter by a factor of the square root of n. As we showed, if I do just a sample size of like 5 here, let's go to 5, I'm going to take 5 points, average them together to get 1 point down below. This is not going to be normal. We need a much larger sample size to meet the central limit theorem criterion. So you might ask me, what meets kind of the conditions? Well, the less normal it is. This right here probably requires about 25, and anything weirder than this might require 100. If you notice, that actually looks pretty good. The less normal it looks. I would call this your criteria for 25 being good enough. That's a really strong skew. If I put something really crazy up, that just looks like something like this right here. This might need more than 25, and let's see what happens. Yeah, that might still have problems with normality. It doesn't look as good as the last one. So we might need something closer to like 50 or something there. But strong skew and things beyond weird and strong skew might need 100. There's no textbook, perfect you need this, but the worse it looks, the bigger the sample size is needed to make it look normal. So let's go back here. Okay. So let's look at this in practice. What does this mean to us? Well, if we're building a balcony, we don't want that balcony to fall apart. And think about this. We have 100 people going to go on the balcony. A recent survey suggests that the average U.S. adult weighs 176 pounds with a standard deviation of 61. Now we can use the normal model to describe this, because when we do this, if we're talking about the average of 100 people, we just take the standard deviation, this is how simple it is, and divide it by the square root of n. And that's easy. Square root of n is going to be 10. This is now 6.1. Our mean is 176, because wouldn't you expect the average of 100 people to be 176 if the Average person weighs 176, so the average would be 176. And our standard deviation for the sample means of sample size 100 is 61 divided by the square root of 100. Square root of 100 is 10. 61 divided by 10 is 6.1. So let's go here and look back at, here we go back in time. We can put this in, I think it was 176, 6.1, and we want to look at it going above 190. The probability of above 190 is 0.011 rounding, so about 1.1%, and we see that here in the coming slides. It's about 1.1%. Very rarely would this happen. We could check our conditions if we wanted. We've sampled less than 10% of people in the US. That's excellent. 100 is large enough to use the central limit theorem. And randomization, we would hope that these people were selected at random. If it's a wedding party, maybe not. And with this in mind, if you're building a balcony and there's a 1.1% chance it's going to fail, you might say, well, that's an outlier, Brian. That's above 2 standard deviations. Yeah, it would be odd if it failed, but it could happen. And so sometimes we got to think in the practical world that this could happen given the wrong combination of people. And then you got to think also, if the balcony says capacity 100, weddings and stuff, people don't like to pay attention to that. So this could be a problem. And we can see here the calculations with the curve below. If below is 0.989, then above is 0.011, which is what I calculated. I calculated the above, and they're calculating the below. So we're just using the normal model right here. So I don't know if I would take this chance. That seems like a bad idea to me. I would not take that chance. It's an outlier, but still, not worth the risk. So what does this all mean? This is where people get confused. We've talked about 2 different distributions right here. This is not saying the more you sample, the more normal your distribution would look. It's the larger your sample size for the distribution of sample means. We've been talking about the distribution of sample means and the distribution of the sample proportion this whole lecture. We haven't been saying like, oh, if you go out and sample 100 people, this is what you'll see for that sample of 100 people. We're looking at the mean of that 100 people, and then we're plotting that mean. In this graphic, let's go back over to that again. In this graphic right here, this is the parent population of individuals. Down here on the bottom is a graphic, and you can see it right here. All these blue dots are obtained by taking 25 samples and averaging them together. And we'll see it drop here in a second. This is just going to be all those averaged together. And that's why this distribution is tighter and more normal. Well, this was already normal, so this is normal too. Let's go back to here. So this is showing us what it actually means. Take any sort of distribution, sample a large enough sample size right here, and your new resulting distribution will look normal. So if we do a large enough sample size with quantitative data, it will look normal. So lots of great stuff going on right here. Remember what this means. This is the whole concept again that we've been repeating, the parent population and what we have going on when we do enough samples, and the distribution will be approximately normal with a mean, and this is of the distribution of the sample means. It'll have a mean, and it'll have a standard deviation divided by the square root of n. And you're just going down 1, 2, 3, up 1, 2, 3, and it looks like a normal curve. Excellent job. Email me if you have questions. And we'll also be doing a kind of online review of this today to make sure everyone is on the right page. Good luck.